Hello everyone, I'm Bradley Sward and this is my Day 16 Part 1 solution to the Advent of Code 2024. The problem is called Reindeer Maze, and for Part 30 of 31 I'm using Python. So the pretty simple problem from a high level understanding. I have a maze. I need to get from the start position to the end position. Wherever I'm starting from, I'm facing east to the right. And basically, if I move in whatever direction I'm facing, I score 1 point. And if I rotate either clockwise or counterclockwise 90 degrees from where I am, I score 1,000 points. And the goal is to figure out what is the path that gets me the smallest score. And so from a high level understanding, that's pretty simple. So in this case, this is 7,036. So basically 7 rotations and 36 moves will get me from start to end. So my data set's a little bigger than that, obviously. I think it's 140 by 140 grid. And the answer I should get is 160,624 is the best solution, which I just showed that I can make happen. Here is my data set. It's humongous, as I was saying. Let me just see real quick. 140, it's 141 by 141. So anyway, so it doesn't much matter, but here's the code that gets it done. So what am I doing here? So basically I'm setting up my file, and so I'm using the stuff from yesterday. If I don't know, but just I'm modifying the stuff from yesterday. I'm going to have 4 directions. East is the direction I'm facing from the start, so I'm just going to say that's the 0 direction. And then I want to make sure again that everything is 90 degrees from that, and I'm using clockwise. From here, I'm going, clockwise, 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 and then I come back around when I want to, come back from here to there. I'm keeping track of what is called a closed list. So basically, I'm keeping track of all the X, Y positions and their rotations as I'm progressing through and trying to figure out and trying to produce the problem or the solution. Because if I basically end up trying to go back to something I've already done, there's no way I'm going to be in a better position because I've already gone somewhere else to come back. So if you think about that, like I'm going to do more work to get back to the same position, so I don't need to continue on and produce more information based on that and keep trying and trying and trying the same position over and over and over again when I know that the smallest number for the steps when I get to that position is what I'm going to want to go for. So I have a closed list. And again, I'm going to set up where is my E, where is my S. Basically, the positions that I'm keeping track of. Here's my Y position, here's my X position, here's the direction I'm facing, and here's my current score. That's where I'm starting from, and then I'm trying to get to the goal. So my best score is a large number because it's going to be whatever the answer is. It's going to be smaller than that. And basically, if I'm going to have a sort, I'm going to sort the positions, as you'll see in a minute here. And after I'm done sorting everything, if the first position in the positions list is basically meeting the goal, well then that has to be, maybe I think I can just get, I can get rid of this if statement here because I don't need to worry about anything like that. I can just say the best is equal to this, and when I fall out, I break out of the loop because I'm only going to find the one solution and it's guaranteed to be the best one. So if I find, because it's going to be the sorted, the smallest number sorted inside the list. But otherwise, if it's not the goal, well then I'm going to try the 3 positions and I'm going to add to the list as I can. And so if I'm going to try to walk forward, I'm going to go, well, I got to make sure that it's not a wall that I'm walking into. And I also have to make sure that the position I'm going to walk into isn't on that closed list because I don't want to add more positions to this thing than I need to because I don't want to gummy up the works here. So if it's not in the closed list and I can walk into the space, well then let's add 1 point to the score, and let's check to see if, this was the closed list, but let's see if maybe we already put this into the positions list. And so if it is, we just want to find out, well, is this score better than the score I've already seen from somewhere else, from some other movement that's going on. And so we just keep track of the minimum of the 2 values. But if I don't find it in the list, well, then I'm going to add it to the list. And basically, I do this for walking, and then I do this also for rotating to the left and counterclockwise and rotating clockwise. Just slightly different here. Like instead of playing with the positions, I'm playing with the rotations, but it's basically the same thought here, but since I'm rotating, I'm already in the square, so I don't have to do the check to see if the square is an octothorpe. And then when it's all said and done, after this is all whatever, I add to the closed list the position on the first position in the positions array or list. I get rid of it from the positions array, and then I sort it again. And then if I do this over and over and over again, eventually I will find my position here. It takes a little while because I'm sure this isn't efficient by any means. But when I break out, I have my best position. It's going to print the solution here at 160,000 something. It'll get there in a second or two. And then I know I have my best solution. Come on, come on, come on. You got this, Python. Come on. There it is, 160,624, which matches up with what I'm looking for. So that's my part 1 solution. I'll look into part 2. I think I'm going to go to bed this time. I stayed up a little too late last night having fun visualizing and trying to make a game out of the voxel project. So anyway, thanks for sticking it out with me as always. Have a great night. Have a great day, wherever you're watching this. And I will catch you in a later video.